So once again, very good morning to all. So the fourth day of the FDP starts with the session on recurrent neural networks. The session will be delivered by our resource person, Dr. Dubey, who has done yesterday's last session, that is on the introduction to deep learning and convolutional neural networks. So without much delay, we request the speaker, Dr. Shivaram, to start the session. Over to you, sir.
Thank you very much, sir. So a very good morning to all the participants. So if you recall, in yesterday's session itself, we figured out that especially in deep learning, there are different type of network in order to work with different type of data. Because based on our application, data may have different modalities. So we found that we can use multi-layer perceptron or artificial neural network in order to deal with the vectorized data. Similarly, if we have the image data, then we can use convolutional neural network, because normal artificial neural network will not be able to handle the matrix data. So otherwise we need to stretch the matrix into a vector form and then we can give the input. But that particular arrangement may have its own drawbacks. Basically, it will lose the relevant information in 2D. Along with the dimensionality problem will be also there. Similarly, a very prominent type of neural network which has emerged in recent past is recurrent neural network. And this recurrent neural network is used to deal with the sequential or temporal data. So when it comes to sequential or temporal data, then what kind of data we can have which can fall in these categories? So suppose if we take an example of speech recognition. So suppose someone is speaking, then the data that we are getting now, that will have the temporal information. Basically, this is signal, this audio signal, and it is going to have these temporal variations. Similarly, if we talk about most of the applications of natural language processing. So in natural language processing, we need to deal with the textual data mainly. So suppose you are you are going to see a movie, and after seeing the movie, there is a portal, and you would like to write some feedback on the movie. So basically you have written some feedback that can be in some words, or it can be in some sentences, or maybe a paragraph. But now suppose if many people are writing such feedbacks, but if we want to sense that what is the sentiment of the people with respect to that particular movie, that we want to get from the feedback. But feedback is in the descriptive form in the sense we have the word or sentences or paragraphs. Manually extracting such information might be very tedious and time consuming and laborious. So if we want to automate such thing, then we need to understand the sentiment of the people who are writing those sentences, just by exploiting the information, by exploiting the relation in between different words, and what are different words which is used. Not just word, even it is also very important to exploit the information or the relationship or the ordering of the words which is used, basically the sequence information. So even suppose if we are writing one sentence, if we just take the words of this sentence and just jumble it, then it is also possible that we may generate some sentence which will not have much good meaning or basically any semantic meaning. So that's where if we want to deal with such type of data where the ordering is also going to play a major role, which was not present in case of the vectorized data as well as the data that we have considered for images. So we were not having such type of requirement there. But this requirement might be the main component if we want to deal with sequential or temporal data. Even in the video also we can have the temporal data video. So suppose if you have a video which is set of frames, now video will have some relevant meaning if these frames are arranged in a particular manner. And again, if you take a video and if we just shuffle the frames of the video, then basically the meaning that could be extracted from the original video, it is difficult to observe the same thing in the jumbled frames of the video. So now question comes that what type of arrangement we should do in existing artificial neural network such that it can exploit this sequential information. It can encode the sequential and temporal information. So this is the key component which is utilized in this recurrent neural network. And why this is important? Because if you see either artificial neural network or convolutional neural network, in both the cases, the dimensionality of the input that we have is fixed. Fixed in the sense, if we have a vectorized data, we are saying that, okay, this is d-dimensional. Then all the data that we are going to use will have the same dimension. Dimension is not going to change. Why? Why changing dimension might be problematic? If you again recall, these deep learning models are built with different layers, and in each layer we have the parameters. Now, how many number of parameter we have to use in the network, that is governed by the information that, okay, how many number of nodes we have in the previous layer. And if we talk about the first layer itself, then the number of parameter is dependent upon the dimensionality of the raw data that we have. So suppose if you're having one instance of the data and your dimensionality is d1, next time if your data is having dimensionality d2, but then it will be problematic. We do not have the provision as of now to have the variable number of parameters in deep learning model on fly. So this is still open research, but as of now, we should have a fixed dimensionality of our input data, then only our model is going to work well. The same thing is also applicable in case of the convolutional neural network. In case of the convolutional neural network also, so what is going to happen? We have a series of convolution layers, and we know that these convolution layers are going to decrease, or even we will have pooling layers in between. It is going to decrease the spatial resolution. So we will start with image resolution, and slowly our spatial resolution will become 1 at the end, and we will have only the values corresponding to number of classes that we have. But suppose if we have designed our convolutional neural network by keeping in mind that the dimensionality of the image that we will get, suppose it is x cross x, then after having 10 number of convolutional layers, we are going to convert that 10 basically dimensionality x cross x into 1 cross 1. But what will happen if suddenly we will get an image which is having much lower dimensionality, which is over much lower resolution, like suppose y cross y, where y is less than x? Then what will happen? Even just after the second or third convolution layer itself, we may basically have this spatial resolution very small, even smaller than our kernel size. Then our system will throw the error because it will not have sufficient input dimension, input resolution to apply this convolution. So that's where whatever neural network we have seen so far, these neural networks always work on a fixed dimensional data. Then I mean the data is going to have the fixed dimensionality. But that is not the case for the problem that we are aiming now to solve with neural network of sequential or temporal. So even if you talk about speech recognition, someone can have the speech of just some 10 seconds, someone can have the speech of 20 seconds, someone can have the speech of 1 minute. So now we have the variable length data. Even the same aspect is also applicable if we are having the data which is coming from natural language processing applications. Like if you have the words or sentences or paragraphs, then we may have the data of any number of words, any number of sentences, any number of paragraphs that we want to deal with. So again, this is very important thing, that how can we deal with variable length data. That is one aspect. And another aspect, how can we retain the sequential and temporal relationship or the ordering of the words that we are getting. That is also going to be very important. So now we will see how these two important characteristic which is required to solve NLP problems is actually included into this recurrent neural network. So in recurrent neural network, we can have different type of recurrent neural network itself that we will see in a progressive manner, that what is the meaning of these different arrangements here. Like we have one to many, means our input is having only one kind of a token and the output is having multiple tokens. Many to one, where we have the multiple tokens as the input and only one token as the output. So we will see through the example that okay, what is the meaning of these arrangements, and many to many. So these are three popular arrangements: one to many to one, and many to many. In many to many also we can have two variants. In one variant, we can start producing the output immediately. However, in another variant, we may first encode the information from one domain, and then we want to decode the information in some other domain. So we will see now some examples of sequential prediction tasks. Now, especially we will be focusing on these natural language processing tasks. And after that, we will see common recurrent units like vanilla version of recurrent neural network and how to train it. And some popular variants like long short-term memory as well as gated recurrent unit, that is called ZRU. So these two are very popular nowadays. And recurrent neural network architectures. After that, we will also see applications in a detail, like sequence classification, language modeling, image captioning, and machine translation. And if time allows, then we will also see a very new concept that is gaining a lot of popularity, especially in RNN, that is called transformers. So now we can have a different sequential prediction task where we can utilize this recurrent neural network. So we have focused over fixed size inputs so far, but now we want to have the variable length sequences. And one example is sentiment classification. So as I already described this initially itself, that if if there is a sentence given to us, then is it possible to classify that sentence into one of the sentiment categories? Sentiment will always, now it is up to us. We can define any number of sentiment classes. Someone can say, okay, I have only two sentiment classes, either it is positive or negative sentiment. Someone can say, okay, I can have three sentiment classes: positive, neutral, and negative. Someone can say, I can have five sentiment classes: very positive, positive, neutral, negative, very negative. So it is again up to us how many number of classes we want to have, but underlying concept is going to be same. So now, so what we want to have, basically, we have these sentences. We want to give these sentences as the input to recurrent, as the input to neural network, and neural network should produce the corresponding class label. That class label can be either positive or negative. So now if you see what could be the challenges here. So there are going to be plenty of challenges in this particular problem. And the main challenge is, how can we give this sentence as the input to neural network? So obviously, if you are talking about the usual neural network, that is the vanilla version of neural network or multi-layer perceptron, then it is very difficult to give input directly these sentences to such networks. So this is one of the problem, and another problem here is that what representation we should consider such that that representation should also encode the temporal relationship or the ordering of the words that we are having. And even many times we also don't have to very strict with respect to the ordering of the words, because so if we are very strict with respect to the ordering of the words, then it is also going to take away the flexibility in order to have the similar sentences or the sentences with kind of a little bit shuffling but giving the same sense or same sentiment by using even different sentences. So, but these are the challenges that we need to see how it can be resolved. So how we can resolve it? Basically, we can include the recurrent concept in neural network, and by utilizing that, we can basically resolve it. So let's see how. So now what we can do, we can process this sentence word by word. We can take one word and then we can give that word as the input. We can give that word as the input to a computational unit. This computational unit is the primitive computational unit, which is also referred as the recurrent unit. This unit will perform some sort of computation. What exactly computation it is going to do? It's very simple. It is nothing but just kind of a projection. So it is just going to do a projection with some parameters. So now we can give the first word as the input to this recurrent unit. Now again, we cannot give the word directly as the input to this particular recurrent unit. Why we cannot give word as the input? Because if you see, the entire computer is working on the numbers. So, but these words that we have, actually these words are built with these characters that might be represented in ASCII. So instead of that, what generally followed in natural language processing, where we have to deal with this textual data, is first we convert these either character or words. It is again our design choice that we are uh, designing our model based on the characters, or we are designing our model based on the words. So based on based on this particular our choice that we are basically processing the words, we need to convert every word into embedding. In embedding, basically feature vector. We need to convert every input into a fixed size feature vector. And how to do that? So there are plenty of approaches for that. And the popular approaches, which is heavily used in the literature, that is called Wordwick model. Means this is kind of a library where you just take any word which is existing in our dictionary, and then that Wordwick is going to give you a vector which is called the embedding corresponding to that word. So whenever we are saying now that we are giving this word as the input to any recurrent unit, it is we are inherently assuming that first we are extracting the embedding using Wordwick or any other model. Like nowadays Globe model is very popular. So Globe model can also give you this embedding. So we are basically giving the embedding, that is the feature vector in a very simple word, that is a feature vector which is given to this particular recurrent unit. So this recurrent unit will generate the feature at the next level, or we can say it is going to basically generate the hidden state. So this H1 is referred as the hidden state after processing of the first word. We have processed the first word. How we have processed this word, that I will describe shortly. So basically we have the parameters. Using the parameter we are doing some computation, and we are producing the hidden state, which is called H1. So sometimes people also refer this hidden state as memory or the context. Basically, it is having the encoding. It is having the encoding of the word that we have processed so far. Because we have processed only one word so far, that is the, then H1 is having the context that we could get from that word, the. So once we get this hidden state, so now this hidden state is also going to be one additional input when we are going to process the next word. And next word that we are processing here is food. So now food is the input, basically the feature representation of the word food using Wordwick or globe model is the input to the next recurrent unit, along with the hidden state that we have generated so far. So H1 and food, these two are going to be now input to this recurrent unit, and this recurrent unit again will generate the hidden state at the next level. So now what could be the physical significance of this H2? So H2 is basically the feature representation, or this is the context information. It will carry the context information that we could get by combining all the word that we have processed so far. It means the food, the semantic meaning or the context or whatever we can say here, the relation, all these information is basically encoded into this hidden state, which is referred as H2. So now this H2 is going to be the input to the next recurrent unit, which is going to process the next word, that is was. So similarly, we will just carry on like this, and once we will reach to the last word, once our last word is processed, so if good is also processed, then after that, whatever feature representation we have, now that is the final feature representation, and this final feature representation will have the context of the entire sentence, or basically it will have the meaning, semantic meaning of the entire sentence in a very abstract way. And then we can use this as the final feature, and using this final feature we can do any task on top of that. So for example, if this is sentiment classification problem, now we can use this H5 in order to perform the classification into different sentiment classes. So we can have any classifier on top of this, any number of classes. Again, all these are dependent upon our application, and we can train the entire model, and ultimately we can perform this classification. So this is the model, which is called a recurrent neural network, where we are going to process each word one by one. So now, so suppose if you don't know about recurrent neural network in past, then you should get confused by this time. And then obviously you should have the question that earlier we mentioned that we cannot have the variable length input for artificial neural network and convolutional neural network, but here we are having the variable length input. And earlier we mentioned that we cannot generate the parameters on fly based on the dimensionality of the input, but that's what we are doing here. How we, because how many number of recurrent unit we are considering, that is dependent upon number of words. Here you can see I have considered 1, 2, 3, 4, 5 number of recurrent units because we have 5 words in my sentence. Suppose if someone wants to process the next word, next sentence, which is the vacuum cleaner broke within 2 weeks. So now if you see the number of word here is going to be 7, then how we are going to basically generate, how we are going to generate these recurrent units even for 2 more words. And in fact, we can have some other sentence which may have 11 words, 12 words, even 100 words. Then how we are going to do that? So basically here we are not generating these recurrent units as a fresh recurrent units. So whatever recurrent unit we have considered in order to process the word the, actually we are using the same recurrent unit. We are using the same computational unit to process the food also. What is the difference? The difference only is that the feature vector which was generated after processing the will be also input to the same computational unit. Why I'm saying same computational unit? Because we are not generating the new parameters when we are processing the different words. We are using the same parameter. So that's where it can process any number of words, because now we are actually doing the repetitive process, repetitive computation using same parameters multiple times in a recurrent fashion for different words. So what is going to change here is how many number of time we are applying this recurrent. That is the only thing which is going to be changed, and that we can control, programmatically based on how many number of words we have in our input. But we don't have to create the new, or we don't have to delete the parameters, which is going to be very good thing, because that we can work with. So we can also take some other application where we can understand this text generation, this recurrent neural network application. Like another application is text generation. So text generation means we want to generate some new text, and that text should be very similar to some training test that we have, basically training text information. uh, let's consider a scenario of a book. So suppose I have a book of let's say data science, and what I want to do, I want to use the content of the book. Suppose we have the ebook where we have the textual information. I want to use the content of that book to learn a model, and once the model is learned, then if we run that model, then the model should generate some text information, and that text information should have a very relevant meaning with respect to the data science content that we have used in the book for the training. So such type of thing can be also done using recurrent neural network. And in fact, this has given a rise to generate even a lot of fake content, uh, because we can use the existing content to train a model, and then at the then we can utilize that trained model to generate new text, which can be a fake text. And in fact, here you can see this is a very nice example, that this deep drum. So if you see all the contents which is created here, these contents are basically the fake contents, but it looks very realistic. So that's what is one of very nice application that we can do on the textual data. So how we can do that? So again, if we talk about the recurrent neural network, so let's uh, let's have this recurrent unit, which is called the tiny computational unit, and then we will have a spatial symbol here, which is called the start symbol. So that is basically just indicating to start. So now this start symbol is given to this recurrent unit, and recurrent unit will generate the hidden vector, that is hidden state h1. So now if you see, this is the different type of recurrent neural network where we want to generate the output from the first recurrent unit itself. So now what is happening? H1 it directly given as the input to any classifier. And what we want to do, we want to generate the first word in the sentence. And the first word which is generated in the sentence here is thus. So next time what we are going to do, the word that we have generated as the output in the first recurrent unit, now that word will be given as the input to the next recurrent unit. Because when we are going to generate the new text in a given distribution, then we do not have any input information here. There is no input at all. We have only a trained model, and that trained model is just going to be used to generate the text information. But we do not have any specific input. We are not saying that if you give this input, then you are going to generate this output. Such thing is also possible. That might be some different application. That might be machine translation application that we will see shortly, where we want to translate text from one form to another form. But here we just want to generate the text information. So then in that particular case, what will happen if I'm trying to generate paragraph, and I have I have already generated first word, and when I'm going to generate the second word, then obviously when I'm going to generate the second word, then the context or the information of the first word should be also utilized to generate the next word. That then only whatever the the sequence of words that we are going to generate will have some semantic meaning, because then it will basically exploit the information or the words which is already generated. So what will happen in this particular case? This thus itself is going to serve as the input to the next recurrent unit along with the hidden state as well. So the hidden state H1 as well as this the first word which is generated, both now will be given as the input to the next recurrent unit. And then next recurrent unit will generate the feature vector or the hidden state, which is referred by H2 here. And then H2 again we can give as the input to the classifier, and then classifier can basically classify into one of the words. Uh, so basically it will find out the probabilities to generate the next word. Then for which word we are getting the highest probability, that will be considered as the output. So the same thing we will basically proceed. Now again H2 will be given as the input to the next label, and whatever word has generated like set here, that is also giving the input to the next unit. And next unit again will generate the hidden state that will be given as the input to the classifier, and we will generate the next word. So we can now proceed in this particular manner, and where we are going to stop. So after generating these words one by one, so now there will be some special word. If that special word is going to come, then we will stop. For example, we can have a stop itself as a special word. So if we generate that special word, it means that now actually we will stop. So by using this, we can generate the text in any given distribution. Why I'm saying given distribution? Because we have to use some ground truth text information for the training of the model. And when we are going to train the model, then what is the next word we already know, because then we know that what is the text information with us. Then in that particular scenario, these next word we already know. That next word is suppose thus or whatever is the next word. Let's consider one more example where we can utilize this recurrent neural network very well. And in fact, this is also the example where we can basically have this multimedia content like images and this textual information both. Basically, this problem is called image caption generation, where we have an image and we want to generate a short caption for that image. So what is the meaning of short caption? It means a very short description that should better characterize that particular image. So here we can see, so we have an image, the first one. So this is an example short caption, which is a cat sitting on a suitcase on the floor. So image description is a different problem. Image caption generation is a different problem. Image description means we can have even longer sentences or even a small paragraph to describe the image. But when we are having image caption generation, so basically we want to generate a short caption, a very short description for that. Maybe that may have some 10 words, 15 words, 20 words max, something like that. So now our aim here is that we have the image as the input, but our output should be the caption. So then what is going to happen here? This problem we cannot solve just by using only one type of neural network. And this is a very nice example where we can see the how we can utilize different type of neural networks to solve some problem having different modalities. So if you see here, this problem is basically the intersection of computer vision and natural language processing, where we have the image as one modality and this text information and as another modality. So if this is the case, Then what is the type of neural network that generally we use to deal with the image data that also require to be utilized, and what is the type of neural network that generally we use to deal with this textual data. This is also going to be utilized. So basically now we are going to have basically our CNN RNN model, and that CNN RNN model will, this CNN model first take image as the input, and it will generate the feature vector, and it is not going to generate class label. We can also generate the feature vector using convolutional neural network. How we can do that? That is very easy to do. So even if you have a convolutional neural network for classification problem, and once your model is trained, you just throw away the final classification layer and just take the output that you are getting just before the classification layer, and that is going to serve a very nice feature vector, and you can do a lot of downstream tasks just by utilizing that feature vector. So in this particular scenario, so our arrangement is going to be something like this, where we have an image as the input, and this image will be first given to the convolutional neural network, and convolutional neural network will produce a feature vector as the output. And then that feature vector, let's represent by H naught. Then this H naught is going to be given as the input to the recurrent unit, and we are also going to have this start symbol. So now if you see here, if you just forget about this CNN and H naught part, image given input to the CNN and H naught, if you just forget these things, then these part, then rest of the things are very similar to the text generation that we have seen. Basically we want to generate the text here, but now, so image caption generation is also a text generation problem, but now this is a conditioned text generation problem. Means this text generation is conditioned based on some additional input that we are getting through the image. So now if you have understood very well that how we can perform text generation using recurrent neural network, then image caption generation is a very simple thing. The only addition in this image caption generation is including this CNN part. Means image is given as the input to the CNN, and then CNN will produce this feature vector. That feature vector will serve as the additional input in the initial recurrent unit itself. So now this is going to generate, let's say, first word, then the generated word along with the hidden state will be given as the input to the next recurrent unit, and then it will again generate the feature vector. Then we will pass to the classifier. We have got the next word. So we will again repeat this particular process, and once we will get this stop symbol, then we will basically stop. So now if you see, this has generated the caption as the dog is hiding. So this is the caption which is generated for this particular image. At the time of training, we already have some sample caption with us in order to train the model. Then we already know there that what is the next word. So here the dog is hiding. So this is already known at the time of training. So there is no problem. However, at the time of generation of the caption on any new image, what we need to do is the first word generated will be treated as the input to the next one. The next second word generated will be given as the input to the next recurrent unit. So like that we will proceed here. So this is again one of very nice example of this recurrent neural network. Let's consider one more example, and which is very much practical in our day-to-day life. So it so happens that we want to translate the paragraph or the sentences or the words from one language to another language, and many times we are taking the help of Google Translator. And even if you would have observed the quality of the language translation roughly 1 decade back by the Google, and the quality of the language translation now by the Google, then you will be surprised. So even I have this experience when I was using this Google Translator roughly 1 decade back. then the quality of that translation was not that much good. And many times we need to edit a lot of things. We need to change a lot of things if you want to translate from one language to another language. But nowadays, what is happening, the translation provided by the Google Translator is almost 99.999% perfect. And most of the time, we don't have to change anything. Whatever is given by the Google Translator is very well correct, and we can just use that as the benchmark. And how we can perform this machine translation, and this basically this recurrent neural network based these technologies have given a great rise to the performance in machine translation. So now question comes here, how we can perform this machine translation. So again, we can use this recurrent neural network, and but now what is going to happen in case of the machine translation? Suppose I have a sentence, suppose I have a sentence written in Tamil and I want to translate that in English. Then what will happen if I take the first word of the sentence in Tamil and if I process that using recurrent unit and I want to generate the first word in English? Do you think that this particular setup will be very good? And first take the first word in Tamil and translate into the English, then take the second word and translate into the English, third word and then translate into the English. Obviously, as per our experience, we can say that might not be very good. And why it will not be very good? Because it might be possible that the first word in one language might be the last word in some other language, or the first word in one language might be anywhere in the in any other language. So it means that the ordering of the word and the arrangement of the word in different languages, even for the same meaning, might be completely different. So that's where the arrangement that we have utilized in case of the text generation, where we can start generating the text from the first recurrent unit itself, that might not be a good idea when we want to perform the language translation, that is basically from one language to another language. Then what is the arrangement which is utilized for machine translation is, let's first process let's first process all the words of a sentence in one language, and let's have a combined feature representation, and then utilize that combined feature representation to start generating the words or the sentence in some other language. So basically, now we can say this machine translation, this recurrent neural network to be used for machine translation will be in two phases. In the first phase, we will process the information from source language into the feature representation form, and then we will utilize that feature representation to generate the sentence in target language. So something like this. So here, suppose we have a sentence in one language, and now we will basically process the entire sentence, and then after that we will start generating the sentence in target language. So now we can try to correlate the input-output scenarios that we have seen earlier, that what are the different applications here that we have discussed can fall in different input-output scenario. Single input and single output. This is as usual artificial neural network that we have seen. So that is vanilla version of artificial neural network, where we have the single input and single output. Then that is feed forward neural network. Multiple input and single output. So if you recall the first application that we discussed, sentiment classification, there the number of word that we have as the input, that is variable. So there are multiple inputs, but what output we are generating? The output we are generating is just a class label. This is either positive or negative. It means that we have multiple things as the input, but only a single entity as the output. So this is multiple and single, like sequence classification. Similarly, we have single input and multiple output, and that we have seen like in the text generation. That is the sequence generation basically. Or even in case of the image captioning also, if you consider only recurrent unit part, then that can be also treated as one-to-many. Once we got the feature representation, then we can basically start generating the sentence. Multiple. So this one we have also seen, even in case of the captioning, this multiple can be used, especially at the training time, because at the training time we need to utilize the these words in the sentences that we already have. So even sequence generation can be also done in the multiple ways, or even captioning can be also done in multiple ways. Multiple, but first processing all the input, then only start generating in the target domain. So this is a typical example of machine translation, the language translation. So now we can have a look over some very popular these RNN models, like original RNN model, which is termed as vanilla RNN, and long short-term memory LSTM, and gated recurrent unit ZRU. So as we have seen, in any recurrent unit, what is happening in any recurrent unit, we have a hidden layer. Hidden layer means basically we have a layer, and that layer is going to take some hidden state from the previous layer as the input, and the feature and the embedding of the current word as the input. It means that it is going to take, so suppose if it is at the timestamp 1, then it will take h0, which is a hidden state from the previous layer. And if there is no previous layer, then we can have some initialization of this h0, and x1, which is the current input, and it will utilize this h0 and x1 to generate h1. And then we can pass this h1 to the next layer, basically next recurrent unit, or we can also utilize this to perform any particular operation on top of that, like classification, regression, or some other things. So then again, we will process at time is equals to 2, time is equals to 3. So if we combine all these recurrent units, then we can now write these recurrent units in a recurrence form. So now here, if you see this particular diagram, at any given time stamp t, if xt is the input, means the word as the input, then what is additional input that we are going to take, that is basically referred by this recurrence, which is ht minus 1. So it means that we will have xt and ht minus 1 as the input at any given time stamp t, and our model will generate ht as the output. It means that we can write like this: ht is the new state, basically that is the feature representation uh, in the tth at the tth time stamp, which can be also referred as a new state. So ht is a new state which can be computed by a function, and that function is parameterized with the parameter w. So w is the parameters of this function, and the input to this function is xt, which is the input at time stamp t, and the previous state, that is ht minus 1. So now if you see, because ht is the new state which is dependent upon the previous state ht minus 1, and we know that such type of relation is called the recurrence relation. So this
Shivram-ji?
okay. Is it audible, sir?
Yeah, now it is. Yeah, thank you.
Okay. So now let's have a look at how a typical RNN is working, and what sort of computation we are doing inside that, and how we can train this recurrent neural network. So here we have a basic Rnn cell, And this Rnn cell is this is a generalized one at any given time stamp t. So xt is the input, ht minus 1 is the previous state. We have the parameters w, and we also use activation function here, that is tanh. So after performing this operation, which is basically the projection using this parameter w, then we can utilize this tanh activation function that ultimately will produce ht as the output. So because now we have two inputs, that is ht minus 1 and xt, so this w will also have two components. So one component will be with respect to ht minus 1 and another component will be with respect to xt. So basically now we can, so tanh, I hope that most of you are aware with this tanh activation function. In fact, we have also discussed yesterday itself. This tanh is one of the activation function which produces the output in between -1 and 1. So now here, this w we can represent in two parts. We can say wx and wh. So wx is the parameter with that is for the input xt. Wh is the parameter which is for the input ht minus 1. So now here, what we are doing in this projection, basically we are doing a simple dot product, and how are basically matrix multiplication here. So in this matrix multiplication, what input we have one matrix w, and we have another matrix which is a combined matrix of xt and ht minus 1. Means we will have xt, we will have ht minus 1. These two are vectors, right? Now we will just concatenate these two vectors. So now we will have a combined vector. So if the dimensionality of xt is n and the dimensionality of ht minus 1 is m, then the dimensionality of the combined vector will be n plus m. And we know that if we have a parametric system, then how many number of parameters we have to use, that is dependent upon the dimensionality of our input. And here our input is having n plus m dimensionality. So our parameter, that is w, should also have n plus m number of parameters. So that's where if you just see one row of this entire w matrix, then it is having n plus m number of values, where n number of values are actually related to wx and m number of values are related to wh. So if I just take one row of this matrix w, which is n plus m dimensional, and this column of this xt and ht minus 1, which is having only one column. So if I just take these two vectors, now by taking these two vectors, I can perform the dot product. So if I will perform that dot product, then it is going to produce one output in our ht. But now question comes here that, okay, how many number of rows we should have in our matrix W, our parameter W? So that is very simple question. That is very simple question here. And why it is very simple? Because we know that what should be the dimensionality of HT. Why we know what should be the dimensionality of HT? Because we are going to use this HT as the input to the next time step. So it means that if we are going to use this ht as the input to the next time stamp, then whatever is the dimensionality of ht minus 1, we should have exactly same dimensionality. Otherwise, there will be problem with the number of parameters. So that's where we have to always retain the same dimensionality of this hidden state. It means that if my h1 is having dimensionality 1024, then h2 will also have the same dimensionality. H3 will also have the same dimensionality. In fact, HT will also have the same dimensionality, which is 1024. But what is going to happen when we are going to perform this matrix multiplication? Then now you can see this xt and ht minus 1, this is a vector, or basically this is a matrix of dimensionality n plus m into 1. However, what is the dimensionality of this matrix W? So we have n plus m number of columns, but how many number of rows we should have? That is going to be dependent upon that. Okay, how many number of values we want in HT? So the dimensionality of HT we want as the same as the dimensionality of HT minus 1, and the dimensionality of HT minus 1 is m. So it means that we should produce m number of values. So now we know this. We know one matrix is having the dimensionality x cross n plus m, another matrix is having dimensionality n plus m into 1. What should be the value of x such that the final output should have the dimensionality as m cross 1? So that is basically very easy to find out. It means that we should have exactly m number of rows in this matrix W. So that's where this matrix W will have the dimensionality m into n plus m. However, but these parameters wx and wh, they are going to treat it as separately. Why it is going to be treated as separately? Because that we will see when we will perform the training of the model. When we are going to update the parameters, then the parameters which belong to wx and the parameters which belong to wh, they might get they will get basically different gradient information. They will not get exactly same gradient. They will get different gradient information in order to perform this gradient descent. So in case of the forward pass, what is happening? We have this h0 x1, which will produce h1. Then h1 x2 will be given, and like that we will proceed. And h1 can be also given as the input to any classifier, and classifier can produce the probability using softmax. So here we can see. So now we have the parameters in the Rnn cell. We also have the parameters when just before computation of the classes course, we can also have one more round of projection using some other parameter, which is referred as wy here. So we can also measure the error based on that, and that measure we can utilize the cross entropy or even softmax in order to measure the error. Then h1 is again given as the input to the next Rnn cell, and next input xt, we will generate h2. So now we will basically just repeat this particular process many number of times. How many number of times? It depends upon the number of words that we have as the input. But what is the key point here is the shared weights. It means that all the weights that we have, that is a W that we are having in Rnn cell 1 or 2 or 3, all these weights are going to be shared. Means they're going to use the same parameter. Similarly, here also this wy that we are considering, that wy is going to be shared when we are processing for different words. So this E1, E2, E3, so these are basically the losses. We can just combine all these losses and then we can start the training. So how we can train this recurrent neural network, that is also another important aspect. And the training happens here through time. Means in case of the deep learning models, we utilize gradient descent based this backpropagation technique in order to train the model. But what happens in case of this recurrent neural network, because we are doing these processing through time, then the backpropagation should also happen through time. So now if you see, this is basically this is the typical structure of this recurrent neural network, and we can unfold it. What is the meaning of unfold? So this is the unfolding of this recurrent neural network. Means if we can write if we can write this computation for a different time stamp separately. So now this is going to be basically unfolded recurrent neural network. So when we are going to perform the backpropagation, then now we will get the gradient, and that gradient has to flow back through time. So that is basically going to be one of the important aspects that we need to deal when we are performing this backpropagation. So this is a typical structure of training module. So first we will have the forward pass. So we will basically forward through the entire sequence to compute the loss. And then we will start the backward pass to compute the gradient. So now, so there is a typical problem or the bottleneck in this particular approach of training recurrent neural network. And the problem here is that how many number of recurrent cell we need to consider before starting of the backpropagation. So that is completely dependent upon the number of words that we have in our input. So what happens? Let's assume that you are trying to learn a model that is for the text generation, and you are having a book. You are having entire book as the input to your model. Then now how many number of words you have in your book? You have several million number of words in your book. And now once your once your model has done the forward pass to that many number of recurrent cells, then only you can start back propagation. And this is going to be computationally inefficient. And why? Because first of all, we need to store all the intermediate outputs that may, because that might be utilized when we are going to perform the computation of the gradient through the back propagation. And that is one problem. And another problem is this time computational complexity as well. So basically, this is going to lead to the problem in terms of both time complexity as well as space complexity. So that's where in practice, the back propagation through time, this is not utilized in order to train recurrent neural network. Rather, there is a small fix here, and that fix is called the truncated BPTT, truncated back propagation through time. It means that what is the meaning of truncated back propagation through time? We will not process all the words in one go and then start the back propagation. That is problematic. Rather, we will basically decide that, okay, I'm going to process 50 words at a time, and then I will do the back propagation immediately after that. And then I will start the processing of next 50 word after that. Means if you're aware with kind of a batch processing, which is generally utilized in order to deal with large scale data sets, then such type of concept is also utilized in this training module itself here. Means first processing 50 words and then doing back to back propagation, means updating the weights itself, and then using the updated weights in order to process the next 50 word, and then again update the weights through back propagation, and then again start the again do the for the next 50 words. So something like this. So run the forward and backward through the chunks of the sequence instead of the entire sequence. So that is basically done in this truncated back propagation through time. So what is the good thing here? So once we have already done for the chunk one, now we can remove everything which is related to chunk one from the memory. We can only read in the final hidden state that we have. And that final hidden state can be used as the input to the next chunk of sequences, are basically words. So now we can also have a look over this recurrent neural network backward pass and how these weights are going to be updated. And the motivation of explaining this RNN backward pass is also more related to the development of this next and updated module, which is called Lstm, because this vanilla version of RNN is having some serious drawback that we can understand if we know that how these RNN models are basically trained, how this back propagation is done here. And then in order to get rid of that problem, we can understand that how LSTM basically overcomes this particular problem of vanilla RNN. So while we are going to perform the backward pass, then we will focus on just one Rnn cell, and the same thing is applicable to all the Rnn cells. So ultimately what is happening, we are getting some gradient, that is basically upstream gradient from the next Rnn cell, which is given as the input here. And by utilizing that upstream gradient, we want to compute the gradient with respect to W, with respect to HT minus 1, and with respect to XT. So let's assume that del E divided by del HT is the upstream gradient, where E is the objective function and HT is basically the output of this Rnn cell. This is the upstream gradient that we need to utilize. And we are interested to compute del E divided by del W and del E divided by del HT minus 1, because if we can compute del E divided by del W, then we can use del E divided by del W to update W. So W is equals to W minus learning rate multiplied with del E divided by del W. But how can we compute del E divided by del W? We do not know all the function here, but we can do that using chain rule, because we already know that what is del E divided by del HT. So we can compute the local gradient first. Local gradient means what is del HT divided by del W. If we can find out del HT divided by del W, then we can multiply del HT divided by del W in del E divided by del HT, then using chain rule, this is going to give us actually the gradient or actually the information of del E divided by del W. And the same thing is also applied in order to compute del E divided by del HT minus 1, which is nothing but del E divided by del HT multiplied with the local gradient of HT with respect to HT minus 1, that is del HT divided by del HT minus 1. So del E divided by del W can be used to update the parameter. However, del E divided by del HT minus 1 can be used as the upstream gradient for the previous Rnn cell. So now, when we are going to compute this del E divided by del W, we cannot compute del E divided by del W just in one go because W is having two components. Some part of the W is actually for the HT minus 1 and some part of the W is for XT. Then we need to actually compute del E divided by del WH separately, and we need to compute del E divided by del WX separately. So now let's write this entire function here, that is HT is equals to tan H of WX into XT plus WH into HT minus 1. So this is basically the computation that is being done by this Rnn cell, where WX and WH, these are parameters, and XT is the input. HT minus 1 is hidden state that we have got from the previous time step. So now what we need to do, we have only this relation. From this relation, we need to compute del HT divided by del WX. We need to compute del HT divided by del WH. We need to compute del HT divided by del HT minus 1. If we can compute these three things, then we just multiply these three things with del E divided by del HT, and our task will be done. And this is not a difficult task to compute what is del HT divided by del WX, because we know what is a function here. So we know that what is the derivative of tan H. So by utilizing that, we can very easily compute del HT divided by del WX, del HT divided by del WH, and del HT divided by del HT minus 1. So then del E divided by del WH can be written as del E divided by del HT into del HT divided by del WH, and del HT divided by del WH is written as 1 minus tan H square, because if you see what is the derivative of tan H, derivative of tan H is 1 minus tan H square. So basically that's what is written here is 1 minus tan H square. So this is the derivative of tan H, but whatever is the inside tan H, we need to take derivative of that as well, and that too with respect to WH. So with respect to WH, it is going to be HT minus 1. So in order to basically satisfy the dimensionality of these matrices, we have to consider it in the transpose 1. So HT minus 1 transpose is going to be considered here. Similarly, we can compute for del E divided by del WX also. Similarly, we can compute del E divided by del HT minus 1 also. So now, if you see here, so this del E divided by del HT minus 1 is basically WH transpose multiplied with 1 minus tan H square, WXXT plus WHHT minus 1, and ultimately this is the local gradient, and it will be multiplied with the upstream gradient, that is del E divided by del HT. Then we will have the final gradient, which is del E divided by del HT minus 1. Now this is very crucial here to understand that what is the gradient information that we are getting from this del E divided by del HT minus 1. So we are having the WH transpose as the multiplication in this entire gradient, and that is basically going to be a problem. So what will happen? So now, because we are going to compute this gradient through time, means first we will compute the gradient with respect to the last Rnn cell, then previous last, then previous second last, previous third last, like that, and ultimately with respect to the first Rnn cell. So now del E divided by del HT minus 1 is computed as del H transpose multiplied with all these terms. But ultimately what is going to happen when we are going to do the computation of del E divided by del HT minus 2? If we do the computation of del E divided by del HT minus 2, then that will also have this term, but it will be WH transpose multiplied with these things multiplied with del E divided by del HT minus 1. And now if you see, del E divided by del HT minus 1 also has this W term. It means that every time we are going to pass this gradient, there will be a repetitive multiplication of the W, because this W is going to come in all the local gradients, and these local gradients are basically getting multiplied with the upstream gradients in order to compute the upstream gradient for the next Rnn cell or previous Rnn cell. But ultimately we are going, suppose if I'm having X number of words, then I'm actually inherently performing the multiplication of W X number of times. And that is going to lead to a problem of either vanishing or exploding gradients. So now we need to understand what is the meaning of this vanishing and exploding gradients. Suppose if this W, which is the parameter which is initialized in the first iteration, before the first iteration, if it is initialized with a value which is very close to 0, then what will happen? Suppose if W is initialized with 0.01, now if I multiply 0.01 some 50 number of times, then what will happen? So this is 10 to the power minus 2. If I multiply 10 to the power minus 2 again with 10 to the power minus 2, it will become 10 to the power minus 4. So if I multiply this many number of times, then ultimately this is going to become very close to 0, and in fact this is 0. So that is called the vanishing gradient problem, because if this multiplication factor is leading to the 0, then ultimately the entire gradient that we will have that will be available for this remaining Rnn cells will be roughly 0. So this is called the vanishing gradient problem. But what will happen? Suppose somehow if in the initialization the value of WH is quite high. Let's assume that the value of WH was 1.5. Then if I do the multiplication of 1.5 50 times, now you can see we will have a very, very large number. And that is going to lead to the gradient exploding problem. So that's where this particular setup of this Rnn, where this gradient is dependent upon the matrix, the parameter value itself, and that too in a multiplicative fashion, is going to lead to either gradient vanishing or gradient vanishing or a gradient exploding problem that is dependent upon the initialization. And that's where it is very hard to optimize this vanilla version of Rnn for a difficult task. So this particular problem is identified in this vanilla Rnn, and it is resolved in long short-term memory, which is another type of recurrent neural network that we will see shortly, that how this is resolved by this Lstm. So in case if there is any question, then you may ask before moving to this Lstm part.
Any queries, sir, to the speaker from the participant side? As I insist, please be interactive, because these are all the concepts, and I knew that Shivaram sir is taking maximum efforts to simplify it so that it will be easily understood. So please interact, and if you have any doubts, or at least put your queries in the chat. Okay, so you can please continue, sir.
Hello.
Yeah, you please continue, sir. I think there are no queries.
Yes, sir. Can you give the share permission, sir?
Sir, in Rnn, in basic, in vanilla Rnn, what is the H0 value initially what we have to select? H1 we can get from that first word. What is the
So
H0?
So H0 we can, because we do not have any initialization, then either we can have 0 values or even we can have some random values.
Some random
Initially.
number. Then you have written in the, sorry, in that Rnn is written followed by H1, we can have some classifier. What type of classifier we can use? We can use classifiers in CNNs or
any classifier. You
any
can use
class.
you can use softmax, you can use even SVM also you can utilize. Any classifier that typically we use that can be utilized on top of that.
I have to get as a output as a word, no? So how I can get the word as the output in from my SVM?
Basically,
Suppose if I
it
am
will
using,
generate, basically it will generate the probabilities for different words. So suppose we have many words in our dictionary, right? Then it is going to generate the probability for different words to be generated as the output. And ultimately, we will consider that word as the output for which we are getting the maximum probability.
probability. Okay, okay. Yeah, thank you.
Sir, I still don't have the share permission. Okay, got it.
Sir, I have one more question. We will face that vanishing gradient problem only in vanilla Rnn or in Lstm.
No. So in Lstm, this is going to be resolved. So let's have a look at that.
Fine. Thank you.
So the next topic is this long short-term memory, which is LSTM. So now here, if you see, currently this diagram, which is just down here in this particular slide, this diagram is depicting a typical Rnn cell, because Rnn cell is taking input xt and hidden state ht minus 1, and it is producing next hidden state as the output ht. So what LSTM is going to do? LSTM is going to insert a memory cell, because the purpose of long short-term memory is to memorize the dependency which can be in the short term or the dependency which can be in the long term. So now in order to do that, this LSTM includes one more cell in this entire unit, which is called the memory cell. And this memory cell is referred by C here. So it is also going to take the memories, it is also going to take the output of the memory cell from the previous state as the input, and it will also include xt and ht minus 1, and finally it will produce the output in the memory cell, which is ct for the next state. So we will build now LSTM in a progressive manner. So here this is not the complete LSTM cell. So what we are going to do, we are going to add one by one what are the different parts of the LSTM and how this is going to influence the entire LSTM mechanism. So now again, if you just forget about this memory cell which is added here, if you just see the initial part in this diagram, that is xt, ht minus 1, and we are basically using a parametric system having the parameter wz, and this symbol here inside, it is representing tanh activation function, basically just squeezing everything in between -1 and 1. So this is the simple Rnn. But now on top of this Rnn in LSTM, one thing that we are going to do is to add a memory cell, and that memory cell is represented by ct here. And this memory cell, what input memory cell is going to take? So right now let's consider that it will take the output of this wz as the input, and it will also take the previous memory cell, which is ct minus 1. So that's why this is represented by a circle here as the memory cell. So now we can say the output of wg is represented by basically the output of this cell is represented by gt. So gt is written as tanh, which is the activation function on the output of this parametrics module, which is wz operated on xt, concatenation of xt and ht minus 1. Now ct we are computing as ct minus 1 plus gt. So again I'm saying this is not the complete LSTM. We are going to modify it one by one. So right now we are including this memory part. We are including a memory cell in the vanilla Rnn. So how we can include that? So that we can include just on top of this GT. So in the GT, now we can add the memory context that we have from the previous state, that is CT minus 1. This is added in this, and now we are having this CT. So now this CT is given as the input. We again have this tanh activation function, and the final output is referred as tanh CT. So now what could be the purpose of this memory cell? The purpose of this memory cell is basically to how much information we should consider, from the previous state that is going to be governed. But how we can control that? Right now it is not there, so we need to include that part. That we will do shortly. Now another important thing which is there in this Lstm cell is input gate. Called input gate, output gate, and we are having this forget gate. So these gates are having different purposes that we should be very clear. So there is an input gate. So what this input will do? So this input gate will also be very similar to this parametric module WZ. This is also parametric. It will have the parametric one. And exactly same input, xt and ht minus 1, the input that we have, the same input is used here as well, xt and ht minus 1. But there is a difference in the activation function. Instead of using tanh activation function, now this input gate uses sigmoid activation function. So this sigmoid activation function squeeze everything in between 0 and 1, means its output is always in between 0 and 1. So this is a very good thing for the sigmoid because its output is always in between 0 and 1. So we can always treat the output of sigmoid as a probability. So the output of this input gate is represented by IT, that is the sigmoid activation function on top of this parametric output, that is Wi operated on xt, ht minus 1. So Bi is the bias here. So now what will happen here? Earlier we computed this GT is equals to tanh h. This we have computed. Earlier we computed CT at CT minus 1 plus GT, but now we are going to have this CT is equals to CT minus 1 plus this GT is going to be weighted by this IT. Why I am saying weighted? Because IT is in between 0 and 1. Then it is actually serving as the weight. And in fact, it is basically serving as the information that because the CT is the memory or the context information which is going to be given, which is going to be provided as the input to the next state. It means that basically this particular expression now is trying to control the information from the current word that could be utilized for the upcoming words or for the processing of the upcoming words, because means how much fraction of the current word we should include in the memory context such that it is basically required in the future. For example, suppose if right now if I'm processing word the, the, so if I'm processing word the, then it is very, we know that if this the word the might not have very strong relevance to the next word or in the upcoming words that we need to process. That in that scenario, our model, our input gate, the parameters of input gate, which is Wi, can be learned automatically in such a way that the output of IT will be very close to 0. And when this is going to be very close to 0, then the amount of additional context that we are going to add in the memory cell will be roughly null, because this word is not going to have much relevance in order to process the coming word. But now suppose I'm processing the word dog. So I have sentence, let's say a dog is running. So if I'm processing a word dog, now this dog might have a lot of relevancy with the coming words that we need to process. Then in that particular scenario, our model can learn in such a way that the value of IT can be very close to 1. Then in that particular scenario, we are actually going to remember most of the information of the current word in the memory cell that could be utilized in the future. So this is basically the physical significance of this input gate in this LSTM. Similarly, we have one more gate in LSTM which is called the output gate. And what is this output gate? This output gate is again very similar to the input gate, but it will have a different parameter. If the parameter is represented by W0, it will take the same input, xt and ht minus 1. And in fact, it is also going to utilize exactly same activation function, which is sigmoid. Means it is also going to serve as a this factor in order to basically do the weighting for something. And in fact, what weighting it is going to do. So basically, whatever is the output of this memory cell CT, and that we have this tanh activation function. Now earlier we had that tanh of CT was the output, but now that tanh CT will be weighted by this OT. So it means what this output gate is going to do. Now this output gate is going to govern, is going to basically control the amount of information that we have now in order to that amount of information that we have based on all the words that we have processed so far. It's not just about one word. HT is H, HT is just 1 second. Okay, sorry. So basically we were discussing about this output gate. So this output gate is going to control the amount of information, means that we have learned based on the word that we have processed so far, and how much information we should pass, basically that we should consider in order to take any decision on top of that, or even to use as the hidden state for the next layer, for the next state. Similarly, we have one more gate, which is called the forget gate. And this forget gate is applied in the memory cell. And the computation of the forget gate is very similar to input gate and output gate. That it will also use the same input, xt and ht minus 1. And it will compute the output as ft, which is in between 0 and 1, because it is using this sigmoid activation function. And how it is going to impact. So earlier we had Ct equals to just Ct minus 1 plus It into Ct, but now we are going to have Ct equals to Ft into Ct minus 1, means now Ct minus 1 is now going to be weighted by this Ft. So what is the significance of this? So if you recall, what is Ct minus 1? Ct minus 1 is the memory context, which is the memorization that we have done so far. Now, if we are going to multiply this Ct minus 1 with Ft, it means that we are basically going to wait that the information are basically the context that we have learned so far, how much context we should retain, how much context we should throw away. So if we want, for example, suppose if we are having this particular sentence, the dog is running in field. So now we have already processed the dog, and we have also processed the running, and we have the context in Ct minus 1. But because we have more words to be processed, and these context might be also helpful for the last word that we have, like running. So in that particular scenario, what will happen? In this particular scenario, we want to retain the context that we have learned so far. Means we have some long-term dependency that we want to retain. So in that particular scenario, what will happen? This Ft will learn very close to 1, such that we can retain most of the information that we have in the context. However, there might be the scenario where the context that we have might not be required for the future. So basically, in that scenario, this Ft is going to be very close to 0 automatically. It will be learned automatically. And then the most of the context that we have learned so far, that can be flushed away. And basically, we can have the new information and the new context that can be inserted through this ZT. So that's what is the importance of this memory cell, that we are learning the context, but we also have the control to flush away, which is not required, basically, which is not having the long-term dependency, that can be removed from this context, non-context, and we can add basically this new context in the memory cell, which is required for the future. So now this is the complete Lstm cell here, which is having 3 gates: input gate, output gate, and forget gate. And the purpose of these gates are different. And basically, but one thing with respect to vanilla version of Rnn cell, this Lstm cell is going to be much more complex as compared to the vanilla version of Rnn cell, because here now we are doing a lot of computation. We are having different gates. Every gate is having its own parameters. Then we need to do the projection of that many number of parameters, and we need to also include this memory cell as well. So those computations are also increased. Even the space complexity is also increased, because we have increased the number of parameters. Even we have increased the memory cell as well. So these are going to lead to the increment in the complexity of the model, but at the same time, this is going to get rid of the problem that we had in case of the vanilla Rnn cell. So if you again recall, the problem that we had in case of the vanilla Rnn cell was with respect to this vanishing and exploding gradient. So now we can see that how this particular Lstm model can get rid of this problem of vanishing and exploding gradient. So this is another pictorial representation of this Lstm. So here we can see we are having 2 inputs, that is ht minus 1 and ct minus 1, as usual. So let's represent this particular LSTM cell at the T timestamp. So HT-1 is basically the hidden state that we are receiving from the previous timestamp T-1. Similarly, CT-1 is the context that we have learned at the end of the T-1th timestamp, and XT is the input in the current timestamp. So what we are doing here, so we are basically first concatenating this HT-1 and XT, and after performing this concatenation, we are processing this through different parameters. Now, these different parameters with respect to the different gates. So for example, we have forget gate, we have input gate, we have output gate, and we also have this vanilla version of Rnn Cell, which is also part of the LSTM. So now here F, I, Z, and O, this is basically analogous to forget, input, and output, and this G is for the original Rnn. And if you again recall what we were doing here, so after getting the output of this input gate, we are multiplying into the output of this GT. So GT is multiplied in the IT, and FT is multiplied in CT-1, and after that we are adding these two things. So the same thing is also represented here, that the output of input gate is multiplied with the output of whatever we have from the Rnn cell, and the output of forget gate is multiplied in the CT-1, and then after that both are added here. So after addition, whatever output we are getting is basically the CT. So CT is equals to FT into CT-1 plus IT into ZT. So that's what we can also get from this pictorial representation, that CT is equals to summation of the CT-1 into FT plus IT into ZT. So that's what is the CT. So now another output that we are generating. So we are generating two output even from the LSTM cell also. One output is the HT, which is the hidden state for the next cell, and another output is the CT, which is basically the memory context, which is also going to be given as the input to the next cell. So now how we are computing the output HT? So HT is computed as the output, which is the multiplication of OT with tan H CT. So that's what we need to do. So CT we have already computed here. So we will pass CT to tan H, and we will multiply that into the OT, that is the output gate. So this is going to give us the HT. So now one question that we had in case of the vanilla version of Rnn Cell, that it was actually having this gradient diminishing and exploding problem. So now we can see when we are going to basically pass the gradient. So now we are having two paths to pass the gradient. One path is via CT-1 and another path is via HT-1. And now here we can see how we are performing the computation of CT. So the computation of CT, we are not having any direct parameter multiplication involved here, because CT is computed just an addition of these two components, which is CT-1 into FT and this IT into ZT, which is basically not having any parameters. So it means that if this is not having any parameters, then we can consider that gradient flow from CT to CT-1 is going to be a very smooth gradient flow. Means we do not have any component in this particular transformation from CT to CT-1 which can lead to either gradient diminishing or gradient exploding problem. So in fact, that can be seen in this particular mathematical representation. So this is the representation here in order to do the computation of a different cell output. So for example, we have the parameters of different gates, for example, WZ and WI, WF, WO. And even if you recall in this Rnn and this LSTM cell, the input that we are giving to all the units, these inputs are always same. It means that this is nothing but just concatenation of XT and HT-1. So the concatenation of HT-1 is given as the input to all the cells. Now we can just represent all the cell in just one matrix form here, having the parameters like WZ, WI, WF, and WO. And what is the activation functions that we are using for these different cells? So for example, if we are having this WZ, then we are using tan H, and for other gates, that is either input gate or output gate or forget gate, we are using this sigmoid function as the activation function. So now this GT is the output. So now this particular thing we can interpret like this, that GT is actually can be computed as tan H operated on WZ into XT and HT-1. However, IT can be written as sigmoid of Wi into xt plus xt concatenated with ht minus 1. So similarly, we can interpret this. So CT is computed as ft into CT minus 1 plus IT into CT. So if we compute the local gradient of CT with respect to CT minus 1, then this local gradient is going to be nothing but ft. And this ft is basically not the parameter. Ft is the output of the forget gate itself. And the output of the forget gate, if you see, this is always going to be in between 0 and 1. So sometimes it may be very high, sometimes it may be very low. So ultimately, we can say that we do not have this particular problem where we are having basically kind of a parameter and we are basically multiplying the same thing multiple times. That is not going to happen in this particular scenario. So that is the advantage of this LSTM over this RNN module, if you see, because now we can pass the gradient from CT to CT minus 1 in a very smooth fashion, and we are not going to have this particular problem of gradient diminishing as well as gradient exploding. So now if you see, but what is the drawback of this LSTM? The drawback of the LSTM is the increased computational complexity, because either we are talking about the time complexity or we are talking about the space complexity. Both the complexities have been increased in this LSTM module with respect to the Rnn cell, and that is the major drawback of this LSTM. Though this complexity is still much lower that generally we have in other type of neural network like convolutional neural network, where we have very deeper architecture, but still by considering the complexity of the problem or the type of the data that generally we use to deal with, we can still say that the complexity of this LSTM model is basically increased. So that's where this gated recurrent unit, which is called GRU, has come into the picture, where it is basically have borrowed the good thing from the LSTMs, but at the same time, this GRU has tried to decrease the complexity of the entire model. And how this is going to do that? So one thing that this GRU is doing is to get rid of this memory cell, but it is still going to rely on the gates. It is going to have 2 gates instead of 3 gates. One gate is the reset gate, and another gate is the update gate. But what is the important thing that this particular GRU unit is doing is to performing this reset gate not on the output of the GT, rather it is performing this reset gate directly on the HT-1, that is the hidden state from the previous time stamp. So now what it is doing here? So HT-1, whatever this is the hidden state from the previous state that we have got. In that, we will perform the multiplication of this reset gate. The concept of the gate is very similar to the LSTM, means these gates are going to have the parameters, and it will take the input exactly same as we have basically in the LSTM, like XT and HT-1. So it's a kind of a merging of forget and output gates into the update gate. So now again, we can just see in an incremental fashion that how these vanilla version of Rnn can be transformed into gated recurrent unit. Means what changes we should do such that it will become the gated recurrent unit. So the first thing that we need to do, so this is vanilla version of Rnn that can be represented as ht is equals to tan h, which is operated on this w into concatenation of xt and ht-1. So now if we are having the reset gate, so this is the one thing that is included in this GRU is the reset gate, which is directly applied on this HT-1. It means that, so if you see in the previous, in the LSTM, we had one output gate, and that output gate was governing this particular fact that how much information of the learned latent vector should be passed or should be used in order to do the final task, in order to do the next task. But that thing we can directly do just by controlling only HT-1 while we are basically performing this computation. So that's what is done here. So this reset gate is directly applied on HT-1. So it means that whatever we are getting now is tan h operated on this W into XT, but instead of using HT-1, now we are going to basically take the fraction of HT-1, and that fraction is going to be decided based on this parametric reset gate. Similarly, we are also going to have one more gate here, which is called the update gate. Update gate will also work very similar to other gates, like it is also going to take the input xt and ht-1. It will have the parameters wz, and it will also have this activation function, which is sigmoid activation function. So the output of update gate will be also in between 0 and 1. And what type of arrangement that we have here with respect to the update gate? So earlier we had this ht dash. Now this ht dash is going to be used in order to generate the final output, which is ht. But now this is going to basically perform the weighting, and it will take some fraction of ht-1 and some fraction of ht dash. It means that now whatever is the final feature vector that we are going to compute, now we are going to basically settle a trade-off between how much fraction of the information from the hidden state ht-1 we should exactly take in ht, or how much fraction we should take from ht dash now. But this is going to be complementary with each other. So that's where we are using these two factors. One is 1 minus zt and another one is zt, such that if we combine these two, then it is going to become 1. So 1 minus zt will be multiplied with ht-1. However, zt will be multiplied in ht dash. So basically, this is just finding out a good trade-off between the information that we can directly carry from ht-1, which is actually equivalent to performing kind of this contextual or the memorization of the context, and how much information we can take from the ht dash. So this is a gated recurrent unit. So in practice, gated recurrent unit also performs very well, but at the same time, it has the advantage over Lstm that its complexity is lower. But in practice, even people have found that many times Lstm performs better than ZRU, because there we have more number of gates, we have more parameters, then obviously we have a complex model in Lstm as compared to ZRU. So now we can, we have already seen this different type of neural network architecture. Even we can have multi-layer RNNs as well, very similar to the multi-layer this neural network that we have. So right now, if you see, this is a typical structure of this recurrent neural network that we have seen, but this is not multi-layer. Many times people get confused that this is the multi-layer RNN. No, this is not multi-layer RNN. This is just only one layer of RNN, but one layer of RNN itself is having the computation in a recurrence form, because actually we are doing the computation on the entire sequence, which is basically having this timestamp. So this is just one step. This is just one layer of the RNN. So similarly, we can have one more layer on top of that. We can have one more layer on top of that. And in fact, we can have any number of layers on top of that. And then we can take the output of the final layer, basically that we can pass to the any classifier, and we can get the probabilities for the classification. So similarly, we can also have a bidirectional RNN. So this is true for all. It can be a multi-layer RNN, or even we can have a multi-layer Lstm, or we can have multi-layer ZRU. So these boxes can be either a simple RNN unit, or it can be a Lstm unit, or it can be ZRU unit. So bidirectional RNN is another extension where right now, if you see, we have coded only from the left to right. So suppose if you have a sentence, the dog is, suppose if you're having a sentence, the dog is hiding. So we have only coded from left to right. But in case of the bidirectional RNN, we can also code from right to left as well. Means we can perform the coding of the sequence from both the directions, and then we can utilize both the information. Means there is one coding from the left to right and another coding from right to left, and after that basically we can combine these two, and then we can produce the probability for the classes based on the combined representation of both forward as well as backward this encoding of the sequence. So again, these boxes can be either simple RNN, or it can be Lstm, or it can be ZRU. So if it is Lstm, then it will become bidirectional Lstm. If it is ZRU, then it will become bidirectional ZRU. Even we can have multi-layer also. So if we just have the multiple layers of the same thing and then we compute the probabilities, then we can say that will become multi-layer bidirectional RNNs, multi-layer bidirectional Lstms, multi-layer bidirectional ZRUs. So we can utilize these basically recurrent unit as and its variants for different problems, and one problem is machine translation, and in fact Google uses this particular for the translation very well. here you can see it basically uses this encoder STMs, which is again, I think you can see this is bidirectional. So the information is coded in both directions, and then basically we are having the multi-layer representation, 8 layers, and then the final output is given to the decoder, and the decoder will basically decode in some other language, and that decoder will also have the multi-layer architecture. So some applications with little bit more detailed, we have already discussed even in the detail, but still we can have a look quickly. Sequence classification we have already seen. We can just give the inputs one by one, and we can use the final output for the classification. Even sometimes we can use the hidden states of all the units, and we can combine it, and then we can use for the classification. That is also possible. We can also perform the character RNN, where we can basically generate the text not by word. We can also generate the text based on just characters. We can have the characters as the input. We can produce next character as the output, and based on that, we can basically train it. So here, these are some text which is generated by training the model for 100th iteration, 300 iteration, 700 iteration, and 2000 iteration. So we can see that after training, it is able to generate the text information which might be very realistic. Even there is some interpretability. So it is also discovered that different hidden units are actually trying to get activated with respect to the different type of information that it sees in the input data. So for example, this particular recurrent unit is getting activated when it finds a code detection cell. Similarly, this is getting activated when it is finding the line position tracking cell, or this is basically when it is finding the if statement cell, or this is code or comment cell, this is code depth cell. So there are different basically units which is getting activated for different purposes. Image captioning, that also we have already seen. In case of the image captioning, we can use SCNN to extract the feature that will serve as H0, and then after that we can have any model, either it is Rnn, Lstm, or GRU, and we can generate the caption. So in case of the caption generation, there is a problem that suppose if any word is generated which is not in line, then it is going to impact other words also in future. So in order to get rid of this particular problem, in practice, for the image caption generation, beam search is applied. So what is beam search? In using beam search, instead of generating just one word, we will generate few number of words. So for example, here we generate 3 words, and then by utilizing these words, we will generate next 3 words. So basically, instead of generating just one caption, we will end up with generating more than one captions with this beam search. But this is basically going to be better because we are relying not just based on previous only one word, we are relying on few number of words which is generated. So the kind of a noise that can come into this generated that noise which can come into the generated caption, that is going to be very minimal, that probability. So these are some captions which is generated. So here the left one side describes without errors, and if you go right, even it is also possible that it may not be able to work well. So even it is also possible that whatever caption is generated is unrelated to the image. So because it is still a very difficult task, because we need to first capture very well what is basically the content of the image, then only we can generate this caption which can be very well with respect to the content of the image. So these things I will leave now in the interest of time. So basically this is the way how we can measure the performance. Even we can basically have the diverse captions that can be generated. So we can include some stochasticity that can be included through variational autoencoder. So again, I will leave this particular part. So this is basically a new thing which is coming up, and it's called attention model, which has given rise to transformer, which is very popular nowadays. So I will not go in much detail, but one thing that I will show here is, so what happens when we are doing this kind of a machine translation or any task that we are doing. So we have the hidden representation of the input, and that we are utilizing to produce output. We also have the context But what happens when we are producing different word in different, when we are producing different words in target language, we are using the same context. So that's where this is not basically, this is not able to exploit, this is not able to exploit which particular word in the input might be more relevant when we are going to produce a word as the output. So that's where attention comes into the picture. So what attention does, attention tries to model this, but attention tries to model this memory context in such a way that what word we are going to generate, it should give more focus to the corresponding word in our source language. And why this is important? Because here we can see. So yeah, so this particular diagram is, you can see this is very important diagram. So now we have one language, and this is converted into some other language. So what happens? It is also possible that we have some few words in one language, and when we are generating the corresponding words in other language, it might follow the same order. So that's what is the scenario there, which is depicted here at the top. So it is following the similar order. But it is also possible that we have some set of words, and in other language, those words are basically reversed, or it is not following the same order. So it means that what will happen, so if I'm going to generate the word, let's say agreement, then obviously I should give more focus to the word accord in other language, because this is highly related to this. But when I am going to generate the word like this European, then I should give more weightage to the European, not to the zone, because zone is the corresponding word from the position perspective, but from the relevance perspective, the important word is this European in other language. So my system should be able to focus more on the characteristic of this one. But in case of the vanilla version of this Rnn, Lstm, and even the GRU, this particular phenomena is not working. So in order to do that, what arrangement has done in case of this attention-based RNNs, that whenever we are going to generate a new word, then we will basically generate, new context. And that context will basically utilize the feature vector of all the inputs, and then it will utilize a softmax function. So softmax function will produce the, and it means that these are the attention scores, which is nothing but it is giving us information about the how much what is the probability, what is the probability that the next word that we are going to generate in the target language should be dependent upon this particular word from our source language. So it means that every time when we are going to generate a new word, we are going to generate the context from fresh, and that context will basically exploit the corresponding word in the source language in a better way. So that's what is the concept of attention. And at present, this attention has basically this is extended to self-attention, and that has given rise to this transformer models, where you have a lot of models like you have BERT, GPT, even there are many models for the transformers. And in fact, these models are also coming in case of computer vision as well. So here you can see, so what is the meaning of this? Suppose if you are performing image captioning problem with attention-based RNN. So suppose if we are generating word, then it is giving more focus to this particular region in the image, means feature with respect to those regions. Suppose if we are generating the body, then basically it is giving more weightage to this particular part. The water, then it is giving more focus to this background. So that's how basically the quality of the sentence that we are generating can be much better if we are having a better attention with respect to the characteristic of the output that we want to generate in the input scenario. So that's how we can use this image captioning with RNNs and attention. So as we are now running out of time, so I would like to stop here. But in case if anyone is interested, you can explore. This is very nice area, and especially these transformers. So nowadays, most of the research papers which is coming in, it is mostly based on these transformers. Okay, so thank you very much. Now, in case if you have any questions, then I would like to take it.
Any questions from the participants?
Sir, is it necessary in input get and output get we have to use sigmoidal activation function, or we can use any other function?
Because the purpose of input gate and output gate is to serve as weight, right? So that's where this sigmoid activation function there is better suitable.
Better suitable. Okay.
You can use any other gate, you can use any other activation function as well. But if it is not, giving the proper weighting, then that might be problematic.
Okay. So 10H also is mandatory in the vanilla Rnn.
That is not mandatory.
Okay. There also we can try other activation function.
Yes, yes. People have tried other activation function as well.
Fine, sir. But these all the models are very complex. We need a minimum GPU, no? Is there any requirement if you want to do
these models are even not that much complex. You can very easily run on Google Colab. So nowadays Google Colab is providing very good services. So all these models you can very easily run on Google Colab.
Okay. Okay, sir. Thank you.
Okay, sir. Thank you.
Any other queries? If you have any further queries later also, you can just email. So with this, I hope that there are no more queries, sir, and I sincerely thank Dr. Shivaram for such a nice session on both yesterday's convolutional neural networks and today's recurrent neural networks. We started from the very scratch, the different types of connections and different types of input-output structures to the recent updates. So thank you very much, sir, for putting everything in a small nutshell and for able to finish in time, started in time and finish in time, and really appreciate your sincerity. And we hope that we'll be having, we'll invite you for further events also in future.
Yes, yes. Thank you very much, sir, for the invitation. And obviously, I will be very happy to be part of any such gathering in future.
Yes. Yeah, thank you.
Okay, sir.
So we'll break now and we'll resume the next session at 11:30. Thank you, Shivaram sir.